Welcome back. Welcome back to theory of probability. So what we are going to do today, we're going to start our discussion on chapter 6 of the ROS, which is on the joint probability distribution of the random variables. So what we have done previously, so we talked about that how to play with one random variable when it is discrete, how to compute its probability mass function, how to compute its distribution and different examples of it. Then we talked about continuous time random variables, how to compute its probabilities and how to compute the distribution functions, and then the different examples of continuous time random variables actually, and their expectations and variances and some of the basic properties of it actually. So now today we're going to move from one random variable to two random variables, or even more than two random variables actually. In other words, that you have an experiment, okay, and in that experiment you identify two random quantities or more than two random quantities. The question is how to compute the probabilities, the joint probabilities of the both random quantities together actually. Okay, so it's going to be the discussion on jointly distributed random variable actually. Okay, that when the random quantity depends on more than one quantity actually. So jointly distributed random variables. So what we're gonna do in this discussion, we'll talk about the theory of jointly distributed random variables when two or more than two random variables are discrete. So theory of discrete and continuous random variables. Okay. Theory of discrete and continuous random variable in joint sense, okay, when you have more than two quantities random in a random experiment. Then we'll obviously talk about some examples of above, okay, and then we will talk about really the examples of above, and then we'll talk about that how to compute say for example the sum of two random variables where x and y follows some probability distributions actually. Distribution. So if they follow some probability distribution, the question is what would be the joint probability distribution for the sum of the random variables actually, or the difference of the random variable. And then we will talk a little bit about the expectation of joint, and then finally we'll talk about that if you have a function of random variables x and y, then what will be the probability distribution of that function of random variable that depends on more than one variable x and y. And then probably we'll in the end talk about the conditional probability distributions in the joint case actually. So what would the conditional joint probability distribution actually. So this is a little bit of agenda. I'll see that how much of this stuff we can cover in today's discussion. So if there will be some more cover, we're gonna discuss in the upcoming session actually. But this is what that our agenda is. So let's just start with the discrete case. Let's imagine that I have two discrete random variables. So imagine I have a sample space omega, and x and y both are two random variables on the same sample space, while x takes say values x1, x2, x3, so on and so forth, and y takes values y1, y2, y3 and y4. Then the notation, then the event, that what is the probability that x will take value x, where x can be any one of these quantities, and y can take value y, where y can be any one of these quantities. So whenever I'm going to put a comma, I'm going to mean and actually. So this is like the intersection of the two events. That one event is what? That x is x and y is y actually. Okay? So, you know, so what is the probability of happening this together? Both, what is the probability that the random variable x takes the value x and y takes the value y? So, as in case of the single variable case, if you have a discrete random variable and you take what is the probability that x takes the value x, you call it the probability mass function of the random variable, what do you call, x. But here, since you have this joint probability, okay, you call such probabilities as this probability, you call such probability as joint probabilities. Okay, so the joint probability of x taking value x and y taking value y, I'm going to denote it by a PDF. But this PDF is not the PDF of only x and y, but the PDF of joint of x and y. So I'm going to use this notation, and I'm going to say that it's a function of two variables x and y, and whenever I'm saying that the function fxy, the joint PDF or the probability mass function evaluated at small x, small y, means that what is the probability that x takes the value x and y takes the value y actually. So you call that probability as this as the joint probability function actually. And obviously there are certain properties that it must satisfy. For example, that all of these probabilities should be something between 0 and 1. Okay, that's one of the things. And the second thing is that the sum, the double sum, okay, of the probability that goes from I equal to 1 to infinity and j equal to say 1 to infinity, and maybe, yes, you can call it j equal to 1 to infinity, of the probabilities of the probabilities of x, y, where x is evaluated at xi and y is evaluated at yj. So all of these probabilities and sum of all these probabilities should be equal to, what do you call, 1. Okay? So, by the way, so once you have this joint probability distribution of x and y, sometimes you also denote this by the vector xy actually. Okay, so you call that, okay, now you have a random variable, but that random variable is basically a random vector. Okay, so it's a random vector. So what values random vector takes? So it takes values, the all possible ordered pairs that you can have from here actually. So in other words, it takes values, say xi, yj, okay, and where I can be anything from 1 to infinity and j also can be anything from 1 to infinity. And for this random vector, this fxy, or this joint PDF, is really a probability mass function actually. Okay, so this is really the basics of the PDF. It's really analog of what you have in one dimension actually. You can extend it. Instead of, for example, having 2 random variables, imagine you have 3 random variables actually, or more than 3 random variables. Imagine you have a third random variable that goes like z1, z2, z3, so on and so forth. Then what would be the joint of x, y, z of x, y, z? So this means that this is equal to the probability that x takes the value x, and y takes the value y, and z takes the value, what do you call, z actually. Okay, that goes like in. And similarly, the joint of 3 should satisfy that since these are the probabilities, so it should stay between 0 to 1, and the triple sum of all these probabilities should be equal to 1 actually. This the same as what you call you have in 2 dimension. And you can extend it, you know, even and you can think of also defining it that instead of having say 3 random variables, imagine I have n random variables actually, x2, x1 and xn. Okay, then what would be the meaning of say the joint PDF of them actually? So that everything is going to be same. Instead you're going to have n sums here and the probabilities should be between 0 and 1. So you can easily extend this theory that you have in 2 dimension on the analog steps, on the same steps to 3 and the higher dimension actually. In other words, to 3 and more than 3 random variables. But I will only stick to 2 random variables. In other words, the vectors, vector consisting of the 2 components are the joint of the 2 random variables, but you can extend it always to more than 2 random variables in the same manner actually. Okay, so the basic ideas are going to stay same. All right. So here is some of the observations. So one of the things, if you know the PDF of the joint of x and y, okay, can you extract the PDF or the probability mass function or density function of the random variable x actually? Okay, so in other words, if you know the PDF, the probability mass function or density function of joint xy, then can we get a PDF or can we extract, okay, or get the PDF of x or y only? In other words, that if you know the information of 2, if you know the PDF of the joint of 2 random variables, can you you know, get what do you call the PDF or the probability density function of say one of the random variables actually? The answer is yes actually. You call such PDF as the marginal PDF or the marginal PDF actually of x actually. Okay, so there is a particular name for such PDF which you extract from the joint of the PDF. How you get it? So I want to know what is that what is the probability that x will take value x actually. So I want to know that the probability that x will take value, what do you call, x actually. Now the question is how to compute these probabilities using these probabilities actually. Okay, all this stuff would be very much clear once you will, for example, see an example actually. Okay, so I'm starting with a bit of abstract theory and then I'll move to the more concrete situation. So when I'm saying that x is taking the value x, the question is, what can be what values the y would take actually. What could be the what could be the values that y can take? The answer is that when x is taking the value x, y can take any value. Okay, so when x is taking value x, y can take value y1 or y2 or y3 or y4 and so on and so forth. In other words, if you want to compute this value, this is same as that you need to compute the value that when x is x and y is what do you call y1, and when x is x r, since when x is taking value x, y can take what value? It can take y1 or y2 or y3 and so on and so forth. Therefore, by the law of the probability, where the probability of the union is equal to the probability of sum, so it's going to be the probability that x equal to x or y equal to y1 and x equal to x or y equal to y2 and so on and so forth. So in other words, in order to extract the marginal PDF of x from the joint PDF, what you need to do, you have to sum up what do you call the PDFs, the probabilities when x is x and y is what do you call yi from I equal to 1 to what do you call, what are the number of values you have actually. So when x is giving you taking the value x, it does not assume anything for y. So hence y can be anything. So therefore you are saying that okay, when x is x, then y can be y1 or it could be y2 or it could be y3, and hence the probability of this should be the probability of sum of all these. And that's a recipe for computing what you call the marginal PDF of the x from the PDF of the joint actually. And similarly, you can have the marginal PDF for y using the joint of joint PDF of x is going to be that okay, it's a probability of when x takes any value xr and y takes a fixed value, what do you call y, and in this manner you can what do you call compute the marginal PDF of x and the marginal PDF of y. Now let's look at these quantities practically from the perspective of an example, and then you can really make sense of it in a more concrete manner. I would like to invite you that whatever I am thinking or the results that I am obtaining or the examples that I am thinking from the perspective of, for example, joint of two random variables, try to develop the similar theory for yourself or think for yourself about the theory of joint for at least 3 random variables actually, okay? Because this is going to give you a good grasp of all these notions actually. For example, if you want to compute the joint PDF, the marginal PDF, where you have 3 random variables, then if x is taking value x, the y and z, the other 2 random variables can take any value actually. So instead of having a single sum here, you're going to have a double sum. One for the I, one for the Y, and one for the Z. So as I'm saying, think about developing a similar theory when you have the joint of three PDF factors, three random variables. So here's an interesting example. So let's just start with an example. Imagine you have an urn. Okay, so imagine you have this box, and the box contains the typical example: 3 red balls, 4 white balls, and 5 blue balls. Actually. Okay, so 3 red, 5 balls, and 4 white and 5 blue balls. And then we draw 3 random balls. Okay, random balls. So in this 3 drawn random balls, imagine X represents the number of red balls and Y represents the number of, say, white balls. Okay. Then on inquiry, on thinking for a moment, what values X can take actually. So it would be a discrete random variable. So either out of 3 random variables, there is going to be no red ball and no red ball. In other words, 0 red ball, 1 red ball, 2 or 3 red balls, and Y can take it can take what values. So it can take that you can have a 0 white ball and 1 white ball or 2 white ball or at most 3 white balls actually, 1, 2 and 3. Okay. So I am interested in what? Computing the joint PDF of this random variable X and X actually. The question is, if X is taking values 0 and 0 and Y is taking values 1 and 2, then what could be the possible outcomes actually? So one of the outcome could be that, okay, you drawn 3 balls and there was no red ball and no white ball actually at all. Okay, so in other words, try to make, so the best way to put it is to make a table actually. Okay, so to make a table. So let's take, say, X that takes values, for example, X, and Y takes values Y, while the small x could be 0, 1, 2, and 3, and small y could be 0, 1, 2, and 3. Okay. Now this point of the table, okay, is representing that what is the probability that there is no red ball and no white ball. So what is the probability of obtaining no red ball and no white ball? Now, one of the things that you have to think is that why I am making this table is because that so if x is taking these values and y is taking these values, then the ordered pair x comma y can take values 0, 0, 0, 1, 0, 2, 0, 3, 1, 0, 1, 1, 1, 2, 1, 3, 2, 0, 2, 1, 2, 2, 2, 3, and 3, 0, 3, 1, 3, 2, 3, 3. So in other words, it's better to put it, so this is like having a matrix actually, which is like a 4 by 4 matrix, with the first entry starting from 0, 0 and the last entry is 4, 4. So this is like a matrix actually. So therefore we made this table. So I'm interested in, for example, this probability, that what is the probability that there are no red balls and no white balls. So imagine, and then what would be this situation? This would be the situation that when all 3 balls are the blue balls actually. Okay, so if there is no red ball and there is no white ball and there are some other balls of other color, then obviously this means that all three balls are of this color actually. Okay, so 3 balls has been chosen out of 5 blue balls. So what would be this probability? So you're going to say that this is going to be, what do you call, the 5 choose 3 divided by how many are the total? So 7 and 5, 12, choose 3. So it's going to be 12 choose 3. Okay, and you can write this number more concretely. So it's going to be 10 by what you call 220. Okay. So similarly, I can ask, what is the probability of having no red ball and 1 white ball actually? So if there is no red ball and 1 white ball, so it means that the 2 balls must be of blue color actually. So this means that, okay, out of the 4 white balls, you have 1 white ball, okay, and out of 5 blue balls, you have 2 blue balls, and everything divided by what you call 12 choose 3. Okay, there is no replacement in this situation actually. So what you're gonna get? So you're gonna get what do you call 40 by 220. Okay, we can think of any probability. Okay, I can think of, for example, what would be 3 2. What is the probability xy 3 2? Okay, what is the probability that 3 balls are red balls and 2 balls are what do you call white balls? You're gonna say, you know, this doesn't make sense because you are only choosing 3 balls. So how can you choose what do you call 3 red balls and 2 white balls actually? So you're gonna say that this has a probability 0. This is not going to happen. So if you are choosing, you know, 3 balls, so there is no way that you're gonna get 3 red balls and 2 white balls actually. So probability of happening this is what do you call 0. So similarly, you can think of all these probabilities, and I can kind of make a matrix. The matrix would look like this actually. So the probability of having 0 blue balls and 0 white balls, 0 red and 0 white balls is, we calculated it, is 10 by 220. Okay, and 1 is 40 by 220. In other words, no red ball and 1 white ball, so it's like no red ball and 1 white ball. Okay, or it should be other way around. No red ball and 1 white ball actually. So it should be, okay, should be here. No red ball, 1 white ball. So it should be, what do you call, 40 by 220. Okay, and similarly all other probabilities can be computed. 40 by 220, 30 by 220, and so on and so forth actually. Okay, maybe I should write, for example, one of the table completely, then leave things for you to do. Okay, what will be the interpretation of this? That there is no red ball. No, there are 3 white balls and no red balls. Okay, so the probability of happening this is because it's going to be 4 choose 3 divided by 12 choose 3, which is 4 by 220, and it makes sense actually. So this is going to be 30 by 220. Okay, and 60 by 220, 12 by 220, and 0. This is going to be 0. Why it is going to be not 12, but this is going to be 18 by 220, and it should be 0. So 3 balls, 3 red balls and 1 white ball. So out of 3 you can't choose 4 actually. Okay, so if you pick 3 balls, you can't have 4 balls. So this must be, what do you call probability? 0, and this is going to be 15 by 220